Hello, people. Let's talk about a special kind of one-dimensional motion. And you can read the prompt here in red. We're talking about an object for which we can neglect air resistance, and it's dropped. That's it. It's dropped and it falls. All right. So depending on your current state of IQ, my dudes right now know that if we draw all the forces acting on this object, all we get is this, a gravitational force. All right? And then my dudes know that if we use Newton's second law, we can say net force equals ma, or Fg equals ma, or, well, this gravitational force can be expressed as m times g, where g is gravitational field strength and or acceleration. That equals ma. And so, not only do we know that since this force is constant, this object, that's the answer to this question, moves with a constant acceleration, we know what that acceleration is. That acceleration is g. This object's acceleration is 9.8 meters per second, which means we can draw a couple graphs representing this object's motion. We can draw a graph of velocity as a function of time. We can draw a graph of position as a function of time. And let me make a little bit of an adjustment on the fly. Or rather, let me not bother doing that. Let's make an assumption. All right, I'm going to make an assumption for the sake of this graph. I'm going to say, let's assume that downward is the positive direction. All right? I'm going to assume that for both graphs. Well, if we do that, first of all, this sphere is dropped. That means that our initial velocity is going to be 0. All right? And we know that this object has a constant acceleration of g, which means that this graph of velocity versus time has a constant slope. This slope is 9.8 meters per second. Right? And again, we're saying that downward is the positive direction, and this acceleration is downward, of course, because the net force is downward, always downward. Now, the graph of position as a function of time, if, let's assume, drop height is x naught is 0, well, this object will start slow and get faster and faster and faster. We know these two graphs say the same thing, because if we look at an instant, say here, we get a small positive velocity. Look at that same instant here, we get a small positive slope. The slope of that tangent is the velocity. All right, fine. And if we look at a later instant, say here, we get a bigger velocity. So here's that instant here. Well, let's look at our slope now. It's much bigger and positive. Yeah, good. But the big deal, all right, the conclusion from this is that when an object is in what we call free fall, right, we're talking about a case here that we call free fall. Let's talk about what free fall means. Well, actually, only. One and only. Only force is Fg. That's it. That's the criteria for an object to be in free fall. And what that means is, no matter what, if an object is dropped or, was at some earlier instant thrown upwards or was at some earlier instant thrown downwards, if you draw a free body diagram for that object, a representation of the forces acting on that object, at any instant, that's what you get. And what that means is, regardless of how fast this thing's moving or in what direction, the same thing comes from this. The object accelerates at the rate equal to g. That's it. And we know also, of course, downward. has gravitational force points downward. Downward meaning towards the center of Earth. Okay, so there are lots of different situations that we call free fall. Free fall doesn't just mean dropped. Free fall means an object is moving under the influence of only the force of gravity. So we'll neglect air resistance for any of our free fall problems. All right? And the big deal is if a question, implies or states this, what it means is that acceleration is g. Typically 9.8 meters per second or 9.8 meters per second squared or 10 meters per second squared. A lot of times, pretty convenient to use 10 meters per second squared. I'll show you why soon. Okay, so here's a few different cases that are all free fall cases. All right, the simplest one, maybe not the simplest one. Actually, none of these are that simple. All right, we don't have case 0 where an object is just dropped. All right, but look, this object, or in case 1, this object is thrown upward. All right, now, what we have to talk about is the instant after this thing, just after this thing is thrown, and just before the thing is caught. All right, we have to talk about the time interval during which gravity is the only force acting on this object. All right, now what I'm going to do here is do a couple of graphs. We'll do velocity time graphs here. We'll do position time graphs here. And the other thing is I'm going to assume, let's assume, yeah, okay, so we're going to assume, here I'm going to assume that downward is the, no I'm not. Now I'm going to assume that upward is the positive direction. Notice I can make whatever choice I want for which direction I call positive. All right, and here I'm gonna still assume that launch / throw height is x0 of 0. All right, so case 1, an object thrown upward and caught on the way upward. Well, here's what's going to happen. Thrown upward. Upward is positive, so we start with a positive velocity. All right, I move some of this stuff? Sure. Thrown upward, caught on the way upward. That means ends with a positive velocity. Here's my V0, that's a V0, here's a V final. And let's say it starts at time 0 and is caught at some time t. All right. Well, this graph is a VT graph of a constant acceleration, so this line has to have a constant slope. That's supposed to be a straight line. Let me make it a better straight line by using an actual line. Yes. So that graph must look like this. Yeah? Fair enough? Now it's red, so you can tell it's case 1. All right, case 2, object thrown downward, caught on the way down. Now, notice in case 1, we know this thing slows down. All right, it's thrown upward, which means V0 is up, but acceleration is down the whole time. So this thing moves in one direction but accelerates in the opposite direction. That means it has to slow down. And gravity makes this object slow down at a constant rate. So therefore that VT graph has that slope. Again, that slope is, well, negative 9.8 meters per second. Since upward is positive and acceleration is downward, the slope of that VT graph is negative. All right, case 2, thrown downward, caught on the way downward. Well, thrown downward means, thrown downward and accelerate downward means speed up. So here's case 2. Let's say it's something like this. Here's a V0, here's a V final. And what this object does is, well, speed up at the same rate that case 1 slowed down, because these two things have the same exact acceleration. All right? But again, case 2, this object speeds up, So notice that V final here, our case 2 green V final, this is a faster speed than it started at. But in case 1, here's the speed it started at, faster, and it ends at a slower speed. But, right, slope equals g. Slope equals g. These two things have the same exact acceleration. All right, case 3, this thing's thrown upward but caught on the way down. Watch what I can do here. I can take this thing, clone, because I know every object has every graph has to have this slope. So let's say that case 3 maybe looks like this. Watch, I turn this one blue. Now we're in case 3, because this says, well, in case 3, I start with a positive velocity, positive meaning upward, right? And then later, at the end, this thing, if we trace back, has some final velocity that's negative, because caught on the way down. And once again, this is the same slope of g because the same acceleration. All right, so we have to be able to interpret from that VT graph, which should probably be in black, this VT graph is that, well, our initial and final velocities represent directions and speeds, but all these accelerations, all these rates of change of velocities have to be the same. All right, the XT graphs, in my opinion, are a little bit trickier, but we have to remember that, let's see, that our slope has to represent velocity. So in case 1, an object thrown upward, that means an initial slope that's positive and big. And this is these objects will all slow down. Well, this object will slow down, but it's caught in the way up, so I mean our initial velocity has to be big and positive. Our final velocity has to be smaller and positive, which means our initial slope has to be big and positive. Our final slope has to be smaller and positive. Maybe that looks something like that. I know I didn't go all the way out to here. It's tough to draw a parabola that's that long. Tough for me. So something like that's fine. All right. For the case 2, thrown downward and caught on the way down. Now I got to break my rule here. I can't really do that because I don't have a negative part of this graph. So I'm just going to ditch this idea. Let's just ditch this idea about that initial spot. But this one, my case 2, I can do something like this. Thrown downward, caught on the way down. That means initially small negative slope, later bigger negative slope. How do I do that? Small negative slope, bigger oh yeah, okay. So how about this? Small negative slope, bigger negative slope. Yeah? It's still part of a parabola. And then blue, notice what I have here. Look at this. The way that I happen to do this, it looks like starting V0 and final V have the same size, which means starting slope and ending slope have the same size, but one's positive, one's negative. So maybe that looks something like this. Maybe this does like, maybe it does like this. Yeah? Yeah, it's all right, not bad. Fair enough? These XTs can be tricky. All right. So, let's look at a few snapshots in time. All right. Let's say that here's an object that falls from rest, you know, or we might say dropped. Well, what's that mean? That means falls from rest. That means V0 of 0, initial velocity of 0. All right. So this thing, let's just say at equal time intervals, let's take like an interval. Let's just call this, how about this? We'll have time intervals equal to some amount of time t. All right? Well, in some amount of time t, let's say that this object falls, hey, do it. falls that far. All right. Well, how far is that? We can express how far that is with a kinematics equation. All right. If we want to know how far this thing has gone, we're looking for what this delta x is. I'm going to call it delta x1. Well, the one way that we can express it is like this. There are a couple ways, but this one works. Watch this. Now that comes from, of course, this kinematics equation, v naught t plus 1/2 a t squared. But because this is a free fall situation, I just put in that a is g. All right. Well, we just said that this thing is released from rest, so v naught times t is 0. 0 times t is 0. And that means that my amount of, well, displacement is 1/2 gt squared, where I'm using delta t. This might be a delta t if we want, but we can just write it as little t. Well, so this turns out to 1/2, all right, fine, gt squared. Now, at equal time intervals, in our second, there's our delta t1. We want a delta t now equal to 2t. So how far does this thing fall in twice that amount of time? Well, here's what happens. We get delta x2 is, forget about this, 1/2 g, careful, 2t squared. So that's 1/2 g times 4t squared. Or it's 4 times 1/2 gt squared, if we just change the order in which we write this stuff. So notice it's 4 times as far as, whoops, I should put a capital there. It's 4 times as far as that first delta x. All right, so where is this object now? Well, if that's delta x1, then delta x2 is 4 times as far. Here's my delta x2. 1, 2, 3, 4 times as far. 4 delta x1. All right, let's change our delta t3 to be 3t. Well, if we want to know how far this thing has gone, we get delta x3 is 1/2 g times 3t squared, or 1/2 g times 9t squared, or 9 times 1/2 gt squared, or 9 times as far as the first displacement. Well, I can't really fit this on here unless I do this, and now I suppose I can. So 9 times as far is like that, sure. So now I have my delta x. Here's my delta x3. That's 4. No, it's not. It's 9 delta x1. So a couple things to notice, of course, these individual from instant to instant distances get bigger and bigger and bigger because this thing speeds up. But because of the relationship between how far this thing goes and how long it falls for, that relationship between delta x and t, we can actually predict very reliably how much farther this thing falls during any additional time interval. All right, and because we know that delta x is 1/2 gt squared, this is a quadratic relationship. So whatever we do to t, we have to do that squared to delta x, which says, notice, if we double the time interval, well, we double squared the change in position. If we triple the time interval, we triple squared the change in position. That's the nature of this quadratic relationship. And here, for simplicity, right, we're dropping the v naught t part. We're dropping this first element here because we're just saying, for this case, let's say, dropped from rest. Okay? Here's another free fall case. This object is thrown upward. Now this is a little, I'm not going to bother with a lot of the quantitative part, but because it just gets a little bit harder to express. But if we say that this thing is initially thrown upward, nope, yep. If we say this thing initially has some speed upward like that, well, maybe after some amount of time t, no, I just want this part. Can I have this part? Yeah, sure. Maybe after some amount of time t, this object has gone, say, that far. Well, in an equal amount of time later, how far is it going to go? Well, not that far, but maybe that far. In an equal amount of time later, how far? Well, maybe like that far. And then how much, in an equal amount of time later, maybe that far. And notice that what we're saying is each of these, here's like a delta x1, here's a delta x2, here's a delta x3, here's a delta x4. This thing keeps going up, but since it's slowing down the whole time, this distance is smaller than this distance. And this distance is smaller than the previous distance. And that distance is smaller than the previous distance. Because on average, this thing is traveling slower per each time interval. So it travels less distance if these time intervals are all the same time interval. All right, and if we were a little more specific about, what this V naught was, right? We could use this expression to say, well, I know how fast it started. I'm choosing, a time interval. I know the value of g. I use that same time interval, and I can calculate what these delta x's are for each time if I choose to. Here we're just saying qualitatively, we know this thing slows down the entire time, so the distance it travels in each time interval gets smaller. Okay, now some actual quantitative examples. All right, a stone is dropped from rest from a 12-meter high bridge. How long is it in the air? So here's where I start. I start with things we know. Dropped from rest. V naught is 0. 12-meter high bridge. That means this thing is going to move 12 meters. I want to know how long it's in the air. Oh, right. This is a free fall case. A is g is 9.8 meters per second per second. Now, here's something we have to pay attention to, even though in this case we could get away with it if we didn't. What we have to pay attention to is the fact that delta x is a vector. Acceleration is a vector. Delta x is 12 meters downward. A is 9.8 meters per second squared downward. All right, V naught doesn't have a direction. I mean, velocity is a vector, but V naught doesn't have a direction because it's 0. But with these two things in mind, what might make sense is let's choose downward to be the positive direction. Then we get to call this positive. We get to call this positive. So we want to know how long, we want to know t. So what's an equation that has these four things in it? Well, an equation that has these things in it is the one we've just been working with. Delta x is V naught t plus 1/2. I'm going to write it as gt squared. Notice since V naught is 0, this whole term goes away. And we want to solve for t. Algebra says we multiply both sides by 2. We divide both sides by g. That would give us t squared. So there's an expression for t. 2 times positive 12 meters divided by positive 9.8 meters per second, and you get what you get. The square root of 2.5. Oh, I don't know, 1.4, I don't know, 1.4 seconds, something like that. 1.4 1.6? Yeah, let's call it 1.6-ish seconds probably, right? Sure. And notice, no magic here, right? This quantity under the radical is positive. If that quantity under the radical is negative, it means you're not paying attention to sign. How fast is this object moving just before it hits the road below? Well, we still get to say this. We still get to say, well, watch this, 12 meters. Let's still call that positive. A is positive 9.8 meters per second, and we want V final. Well, there is an equation that has those things in it, and it's this. V squared is V naught squared plus 2G delta X. That goes, and so V is the square root of 2G delta X, and V is the square root of 2 times 9.8 meters per second squared times 12 meters. Again, these things are both positive. No magic where we have to disregard some signs. So that's the square root of 240-ish. Let's call that, oh, it's the same, isn't that like, oh yeah, it's like 16 meters per second or so. Now here's something that's pretty neat. Check this out. Because there's a different way you could solve this problem. You could also use this result with this, and you could say that V final is V initial plus GT. V naught is 0. V equals 9.8 meters per second squared times 1.6 seconds. Here's where it's real convenient to call that about 10. So if something accelerates from rest for about 1.6 seconds, it's going to end up at about 16 meters per second velocity. So, is it always that you can just use kind of whichever equation? Absolutely not. You have to decide what set of givens you're using here. Those set of givens lend themselves to a single equation. Here we chose, we were lucky here, we had a couple ways to do it, but with our initial givens, this is the only equation that has those initial givens in it. But because we found this answer here, maybe we get to use a different set of givens and therefore a different equation. All right? This will address, so here we're trying to write some expressions without numbers in terms of things like t amount of seconds, and using like g as an acceleration. So see what you can come up with for expressions for these. This is v naught we're looking for. This is delta x we're looking for expressions for those quantities. All right, I'll see you soon.